This book was found by my son a few days ago in a second-hand books. Two Russian journalists were wandering around Russia in the 60s. It was 1964, and interviewing scientists and writing like a report of encounter with the 21st century. And of course, they are dedicating a lot of information about education in general. One of the most fun areas is the way they describe the new school of the future. And of course, there is there the profession of the future. For instance, the most popular profession there is remote managing of mines. Like they were still in the age of thinking about mines as the most frontier. So the most advanced application was like mining in remote way. And of course, there was their AI that, according to this book, was supposed to do whatever we do, but much faster, like an amplifier. And this is, I think, one of the most often reactions that we see for AI in education. We see it as something that will take whatever we do as humans, but make it much more faster. Another attitude that was mentioned by Cecilia is being terrified by the new technology. This is a poem that was written by a teacher in 1920, like 100 years ago exactly. And he's terrified from new technology. For him, new technology is radio, moving pictures. Edison is the evil, and the vision that he sees in front of his eyes is actually the idea that education will become to be a matter of pressing a button. And perhaps I, as a teacher, get a position as a switchboard. And I think this attitude, as the first one, is a very common one. We try to give interpretation for new technologies based on the way we are acting today. And then the interpretation could be or amplifying the existing world or terrifying the existing world. But we cannot really imagine something different from the daily practice that we have. And actually, I think the best metaphor for maybe the way we should look at new technologies in general, and particular in AI, is the transition that we saw between photography and painting. Actually, photography did not make painting unneeded, but it redesigned it. Like the first photographies that we can see in the 19th century are exactly like painting. They took the same kind of positioning the images. They did exactly the same function. And it took some time for photography to understand what it can do different from painting. But I think the interesting thing is that it took some time also for painting to understand what do we need painting for in the age that we have photography. And one of the nicest examples is this work of Degas, and in general the work of Degas, which uses light and color in a way that could not be used before we knew about photography. Like this way of freezing a casual situation is something that we did not do in the age of just painting. And following this metaphor, we should ask ourselves, what can we learn about learning from this age of AI? And I would suggest that as opposed to going to looking at AI as a tool, we should look at AI as a source of creating a new narrative for learning. And narratives for learning, as we all know, are very, very important. Actually, schools and educational systems were designed and were engined always by big narratives, by big stories. It could be religion in the Middle Ages and later. It could be science after the Enlightenment. It could be a more, let's say, commercial world in our age. But we need some kind of principle that leads the way we work, and each principle like this has some unseen principles that are really managing the way we proceed. And one of those unseen principles, I think, has to do a lot with intelligence, which is the word we're using when we try to speak about a clever machine. And before trying to understand this narrative, we should ask ourselves, what do we mean by intelligence? And I think usually when we are referring intelligence in the sense of artificial intelligence, we're speaking about accomplishing tasks. We're speaking about accomplishing goals. And in this sense, a mouse can do much better than a spider, and a chimpanzee can do much better than a mouse, and a human being can do much better than a chimpanzee. We are much better in creating tasks. And of course, artificial intelligence is in some areas much better than us in accomplishing tasks and reaching goals. And when we ask ourselves what makes us to be better, what makes human beings to be better than cats or mouse, I think part of the answer is probably this character of us of asking questions. And I really love this quote of Kurt Vonnegut that says, tiger go to hunt, bird go to fly, men go to sit and wonder why. Tiger go to sleep, bird go to land, man go to tell himself he understand. And this quote, I think, should be read very carefully in its both sections. First of all, this tendency of asking questions really is a real game changer. We all the time curious, and when we ask questions, we discover more and more abilities to accomplish those tasks that we were speaking about. But also, we need the understanding. We cannot just stay in the position of asking all the time. We need some kind of place to rest. And our place of resting is telling ourselves that we understand. We are not necessarily understand, but we are telling ourselves that we understand. We need this way of managing the world. And these two aspects, asking and understanding, or telling ourselves that we understand, are crucial for education. Like, I think they are some part of let's say, the building blocks of every process of learning. And when we look about our practice of learning, there is a lot of reasoning there. And the fact that we have reasoning, of course, helps us to get accomplishing better outcomes, but it also has a big narrative there behind. Like, there is reason for everything. I think it starts back then in Socrates or Plato, that teaches us that we cannot really lean on bare facts. We have to give some reason. The reason used to be the myth. It could be afterwards based on science. But we have to bring reasons for things, and we have to explain things to ourselves. And going now to AI and trying to understand what is the reason, the way AI changes this kind of a narrative, I think we should go back to Claude Shannon. Beforehand, Ovi mentioned Alan Turing. I think the other big name that we should all be really appreciating and admiring is Claude Shannon, the father of the information theory. And Shannon, in the 50s, wrote a very interesting article about how can we program a computer that can play chess with a human being. We should remember that back then in 1950, probably the computer was made out of stones and paper bags, but still he had this ability of predicting the way AI will be functioning, and he was presenting two types of AI. The first one, which we can call a brutal AI, is actually not a very smart machine, but a machine that can do a lot of work. Like, speaking about chess, it's an algorithm that can go move by move and really scan all the possibilities, and if he's fast enough, he can defeat a human when he does this Sisyphical process. The other one is really focusing on a small number of moves, but the right moves, the moves that can really make a change. Of course, the B type should be much more smarter, like should understand something which is not just going step by step. And Shannon thought that if you want to imagine a stage in which a computer is defeating a human being, it will be probably the B type, not the A type, because the computer power that we know is not strong enough. And we know that for an average chess game, there are lots of possible moves. And of course he was wrong. Like the computing power evolved much faster than we expected. And when Kasparov was defeated by Deep Blue in 1997, he was defeated actually by A-type AI. He was defeated by not a very smart intelligence, like Kasparov himself said, more like programming my alarm clock. But this alarm clock was so strong that he defeated the champion world. And going forward 19 years, we also found the other kind of AI, the B-type, and I think the best symbol of this is probably the AlphaGo that won the Lee Sedol, the world champion in Go. As you all know, Go is extremely complicated game, much more than chess. I cannot even pronounce those numbers in English, but it's big numbers. A lot of moves, much more than the atoms of the universe. And the way AlphaGo was able to really find the way to defeat this champion was through analyzing a lot of different games, about 160,000 real-life games. And after eating all those games, he really was able to suggest moves that were never seen by a human being. It was not way of a human being thinking, and this is why it's really unique. This is why this is a B-type of AI. It really suggests a new way of thinking, a new way of creating ideas. And the most, let's say, dramatic event afterwards was the fact that even the AlphaGo was won by the AlphaZero, and the AlphaZero is another stage. He's not anymore learning from other games. He's training himself. We are not teaching him anything. He's teaching himself. And this all process, of course, we're speaking about a game, but we could bring an example from science. Those scientists from Cornell University, Hod Lipson and his student, have created a pendulum that was learning through the movements lots of physics rules, and the legends say that when they went out to eat lunch and when they came back, he was already discovering the second law of Newton. And we all know the story about Tai, the Microsoft chatbot that was still learning from the crowd and became to be a cursing machine. And all those examples are really examples that shows that the information in this age is not anymore something which is based on the way that we are doing reasoning. And actually, in a way, we can see a gap between understanding and reasoning. We see things that we cannot anymore understand, like the Go example. We don't know exactly how this guy was defeated by the machine. We know how, roughly how the machine learned, but we don't know to justify any move. And this is a very dramatic change in the narrative. Copernicus back then in the 16th century was chased by the church, not just because he was suggesting ideas that the church did not receive. It not was about astronomical theory, about the fact that the Earth is not in the middle of the universe. It was about the self-image of the human being. Like Copernicus taught us that the planet that we are living on is not the center of the universe. We are actually moving like any other planet in the same way. And the same goes to Darwin. Darwin again. Darwin and the evolution is not a biology theory. It's a theory that says something about the human being. This is why it's so scary for everyone. This is why even today we see schools and educational systems that are fighting this theory, because it's really changed the way the human being understands himself, and this reflects science and reflects education. And I think AI should be positioned in the same place. Like the fact that there is knowledge and there is a way of reaching goals, which is not going through a reasoning, but something that we can really explain, we can test, we have rules or models that can justify, is a really dramatic phenomena. And Henry Kissinger, 95 years old guy, published about 2 months ago a long article about AI. First of all, unbelievable that the guy in this age really has this perspective of understanding all these elements, but I think he brought a very interesting observation in the end of his article, saying that as opposed to the Enlightenment age that had, first of all, had a philosophy and then developed technology based on this philosophy, in the age of AI, we have a technology and now we have to figure out what should the philosophy will look like. Thank you very much. And now, moving from the philosophy side, we are getting closer really to touch and try to understand this elephant in the room. And the next speaker that I would like to invite, Jonathan Laserson. My first encounter with him, and actually the only encounter with him, was through a podcast. I heard him speaking for 2 hours about AI and machine learning. And it was so fascinating that I arrived my home in the Negev desert, and I stayed in my car instead of entering home just to hear the end of his podcast. He's really have a very clear way to really mediate this field. So Jonathan, please, welcome.
Hi, thank you. I'm humbled. So I can barely see you guys. I'm guessing that a lot of you have heard about deep learning recently, right? How many of you? Let's have a show of hands. How many of you heard about deep learning? Yeah, a lot of people. Good. Because 2 years ago, 3 years ago, it wasn't really like this. Deep learning. Did it work? All right. Deep learning is responsible for quite a few breakthroughs in the last few years. And there are two very big major movements that deep learning is a major enabler for them to succeed. For example, autonomous car driving. It's one of those big movements that's going to shape our lives in the future. Another one is medical imaging and generally the medical field. I'm working in a company where we look at medical images and we try to diagnose those in the way that a radiologist does. For example, pneumothoraxes and fractures and all those things. And this revolution enables all this breakthrough. It's quite special, and it's different than what I've witnessed when I did my PhD. This revolution is not led by the academic world. It's led by all these big technological companies who publish papers even more frequently and more often than in the academy. And one of the other things that all of these big companies have their own framework that enables people, engineers like me and researchers to do AI, every one of those. And another thing that's really special about this revolution is that it's highly accelerated. And one of the things that's different is that when someone produces a new paper, they no longer wait for the conference to have it published. They publish it immediately to this website on the bottom right, the archive website. And it's not even peer-reviewed. They just put it out there. But along with that paper, they staple to that paper the computer code that generated the result of that paper. So think how much this accelerates the field when someone is producing a paper and the day after, anyone in the world, any engineer in the world can take that code and actually see what was really done and how they got the result. And as a PhD student 10 years ago, even learning, even in the AI field in machine learning, it wasn't like that. So we are deeply accelerated because of those things. So I'm glad that Avi and Cecilia that you mentioned AlphaGo, because 20 years have gone between since the time that Deep Blue, IBM's computer, beat Garry Kasparov in chess, to the time that we beat that AlphaGo, Google and DeepMind's computer beat Lee Sedol, the Korean champion, the world champion in Go. Go is considered to be the Everest of the board games. When human players play Go, a lot of time when you ask them about why they did a certain move, usually they say, we don't know, it was intuition. So when people ask, when we built the machine, we, Google and DeepMind, of course, built the machine that beats Lisa Doll, a lot of people said that we actually built something that works more like an intuition. What is really an intuition? What is the intuition? Intuition is the type of knowledge that we have that we cannot communicate with each other. This type of knowledge is stored in the hundreds of billions of neurons in our brain in a way that it's a knowledge that we have in a subconscious way. It's something that comes up to us immediately without really requiring us to think about it consciously. So the difference between 96 and 2016 is exactly what Avi said. It's a different type of approach from the A approach that was merely brute force to the B approach, which requires more intuitive kind of thought. And I'm going to try to convince you in the rest of this talk that we really are zeroing in on some aspects of how we humans do some type of, the subconscious thinking, the intuitive thinking. So one of the things that we can do, there we go. We can look at an image and we can immediately say, this is a person, this is a dog, this is a chair. We don't really have to think about it. And of course, what we see and what the computer really sees is something that is kind of like pixels. We see these intensities of light in a particular point in hitting our eye. We're not really seeing immediately, we're not really, the original information doesn't come as these bounding boxes over people. So, sorry. So what really happens is that information, the visual information comes from our eyes to this area in the back of our brain that's called the visual cortex. The visual cortex is part of a larger part of the brain that's called the neocortex. And all of our visual information processing happens here in the visual cortex. And the first layer of the visual cortex, the first processing layer is called V1. Now, these two scientists, Hubble and Wiesel, won a Nobel Prize on their research on V1. What they did is they put a cat in front of a monitor, and they tried to figure out what makes the neuron of the V1 layer tick. So they have this cat sitting in front of the monitor, and they have an electrode listening to one of those neurons in V1. And when a neuron fires, you can actually measure it because the level of the electricity is rising. And they try to figure out what makes him tick. They put their triangles and circles and a lot of shades of light, and nothing really worked until one of the most amazing eureka moments of science in the 20th century happened. They figured out that this neuron fires whenever they put in the slide into the monitor. So it was the shade line of the edge of the slide that triggered out that neuron, which we now know is called simple cell. So that neuron fired when it saw a particular line at a particular angle at a particular part of space. And when they further investigated, those cells, they figured out that when they changed the angle of the line, that neuron stopped firing, but the neuron next to it started firing. Or when they kept the line in the same angle, but they moved it a little bit up or a little bit down, that neuron ceased firing, but a different neuron started firing. And what they figured out is that part of the brain had an area of neurons that was, you could say that they were spread on two different dimensions. One of them was the angle of the line, and the other one was the location of the line, the segment, in space. And now think about what it means. It means that after the information from the eyes, the pixel type of information, goes through V1, after that point, the brain doesn't see the world anymore through pixels. It sees the world using different concepts, different representations. From now on, the brain sees the world as line segments in different locations. And you can think, why was this useful? Why is this important to have this type of representation? But it's something that the brain does. From that point on, after V1, we no longer see the pixels. We just see those lines. So why those lines? Why not other representations? Olshaus and Fields are two different scientists who tried to answer that question. So they did a simulated experiment. They took thousands or tens of thousands of what they called natural images. So those are images of lakes and trees and ponds and mountains and so on. And they took hundreds of thousands of small patches from those images, 24 by 24 stickers. And the questions that they tried to answer was, what are the most important basis elements of these patches? So they formalized this type of problem, computational, mathematical even problem. Let's say that you are a painter, and your goal is to recreate each one of those hundreds of thousands of patches. But you are constrained to use only a specific set of stickers. So you're a painter, and the way for you to paint is to put stickers on top of each other. So for example, if this is a patch that was taken from one of the images, you might take the circle sticker and you put the triangle sticker on top of it and the next sticker on top of it, and then you'll create a patch that is based on those three stickers, one on top of each other, which is kind of going to resemble the original patch from the image, but it's not going to be exactly. And they formulated a mathematical problem that will require us, that basically asking us what is the best set of stickers that we can possibly have to be able to recreate as many patches as possible, as accurately as possible. So I remember actually running this algorithm, and you can see the 64 stickers, and it starts from random noise, and then with every iteration you see these stickers forming up and being like more concise and more particular. And do you have any guess what they're going to find out? These are the 64 stickers, lines at particular places, at particular angles. So this is actually a slide from the papers. And on the left side, you see one of the patches from the image, and that patch from the image can be reconstructed using these three stickers, like a linear combination of these three stickers. Not going to go deeper into that. But that was a major breakthrough, because after reading this paper, I felt that a loop was closed. I felt that we finally found a mechanism that is shared both between our brain and something that we can, basically that we can simulate on top of the computer, that we found some underlying truth. And this got me particularly excited, because if this is V1, and V1 is the layer that the brain processes the information after only 40 to 50 milliseconds, then what happens in V2? What happens in V4? What happens later on? And we have all these guesses about maybe it's these corners or little circles or maybe other aspects. And you know something, it took 10 years until something like 2006 until we had some answer to that. And that answer involved building a neural network that was able to have a bunch of layers in a very similar way to how the brain is kind of orchestrated. So do you want to see how what the brain sees in the other layers? Yeah, let's do it. So it took years to be able to see this, and I got really excited about that. So the first layer, and by the way, this is computer generated completely, right? This is basically doing reverse engineering of a neural network. The first layer always sees lines at particular angles. Then in the second layer, you start to see some textures. In the third and fourth layer, you start to see some emerging patterns. And in the fifth one, you already see something that looks like parts of objects. Maybe some buttons over there, flowers over there, maybe something that looks like noses of dogs, something like pillows, like ants, I don't know. In the higher layers, you start to see something that looks like objects. Buildings, eyes, dogs, a lot of dogs in those data sets. So this is what the computer actually sees. This is what the neurons of the computer actually sees. And what we're seeing here is the process of conceptualization. No one told the computer you should see a dog. The computer, the algorithm found out that it would be really useful to solve the particular task it needed to solve, to have a neuron that will represent the visual stuff that it sees, a visual representation for a dog. So this conceptualization process is what really is the new message of this technology. Because in the past, we, the engineers, the humans, had to tell the computer, if you look at an image, you should pay attention to the edges of that image. That's really important. And when we played an audio to a computer, we used to really differentiate it to different frequencies because we thought this is the right way to represent sound. And when we took text to a computer and asked the computer to say something about the text, we already turned it into subject and object, and we showed it all the parsing trees according to all the computational tools that we had. The new message of this technology is we no longer need to do this. I'm not going to be presumptuous to be able to tell the computer what is the best way to represent the data. I'm going to let the computer do it itself, and I'm not going to tell him, I'm not going to assume that I know better. And that's got us to all these improvements. So now we're going to have some fun. Neural networks, not only, after you have this conceptualization, neural networks can actually generate stuff. So these faces were generated completely automatically just by showing a lot of faces to a computer. And the algorithm was able to generalize and generate new faces. This is an amazing work by NVIDIA. This is work that I did. So I implemented an algorithm that I taught the computer the Bible, basically, the Bible text, and asked him to predict the next word. And then I just started letting the computer predict words and words and words. So you see these basically lots of new chapters of the Bible that I was able to generate automatically. It made sense to me pretty much as the Bible did, all these punctuations was generated automatically just by having the computer see all this biblical text in Hebrew. This is something to the educator might be remind you of something that happened a few years ago. The Prisma application, you give it an image, this one from Tel Aviv, and you gave it some artistic style, and the computer can turn the image to be of that particular style. Amazing stuff. Is this art, by the way? I don't know, but this is something that we can use. And this is really recently, and this is what I'm going to finish with. Once we can do this style transfer from image to a different style, people did it for video. So they have this dancer on the top left, and they can extract the pose. Thank you, yeah, play. They can extract the pose of the sound, actually. You can make the sound work. That would be great.
Lucky for you, that's what I like.
Yeah.
That's what I
And then
like.
these two
Lucky for you,
PhD
that's what I
students
like.
get animated according to how this pose. So think about the future when we create not only, we can create fake videos basically, not just fake news. Thank you very much.
Thank you, Jonathan. And I didn't mention before, but Jonathan is also a PhD graduate from Stanford, and also our next speaker, Dr. Oli Foreman, came from this university. And Oli is also an entrepreneur previously, and today in language team in CET. And Oli will be talking with Bob Rosenshine, which is kind of a legend, I think, in the short history of startups in Israel and abroad. And I think his long career is really a way to have a very wide and interesting perspective about the landscape of the evolving of AI and the usages that can be done in this world. So please, Oli and Bob.
It's exciting to have Mr. Bob Rosenshine here on the stage, and it's a really exciting time of big data, even huge data. We can create a sequel to the Bible with big data. So there are many answers out there, but we all know that to get to the right answer, we need a very intelligent question. So my first question to you is, what kind of intelligence were you relying on when you were founding Answers.com?
First of all, thank you for having me today. When we founded Answers.com, and I want to acknowledge Yossi Vardi, who both gave me the idea for Answers.com, was an early investor, and helped us profoundly at many stages. It went through several shifts, you would call it pivot. First, we started out with very, very simple factual encyclopedic information. But the pivot we did that made the most sense was to user-generated questions and answers. So we had a situation where people would put in any question, we can talk about the different kinds of questions, and other people could not only answer the questions, but edit each other's. So we were the Wikipedia of questions and answers. The other thing we learned how to do was basically judge the quality of the questions and the quality of the answers through the user-generated process. So there are many kinds of questions. There are simple factual questions, 2 + 2, how many pounds in a kilogram? What's the weather in Tel Aviv tomorrow? These are easier to answer. The harder ones require more judgment or multi-stage or more complex information. And what we found the most interesting ones were the ones that blended opinion, background, depth, and length. So we had to develop a system, we called it REMUS, which basically measured automatically and through user input signals, both what we called, it was ADQ, which was answers document quality, and AAK, which was answers author karma. And we came up with an SEO improver, basically, which was able to get the best questions and the best answers, the most exposure in the system.
The users actually rated both the questions and the answers, so that way you intelligently...
There were many ways, there were many signals to this machine. Basically, we got a lot of traffic from Google. Google, in those days, believed very much in keeping you on their page as short as possible. Okay, so you went to a Google search page. We also had a very special relationship with Google, where for about 5 years, we had a special link in the corner of every Google English result page with a reference in the corner to answers.com, basically. So we got a lot of traffic from them. But what they did is spidered and indexed our pages very successfully. So I'll give you a very simple example. We would get on the order of a new automotive question every 26 seconds on the average. Okay, someone would ask, where is the air filter in a Mazda 6? Okay, a very specific question. That question was asked, someone else may answer it, Google indexed it, and anyone in the world who would want to know the answer to that question would find it. That would be a factual question, but a very specific one. And we found with the more questions we had in the system, the more answers we had, the more answers, the more traffic. So it was a virtuous cycle, which would give us an opportunity. Some of the other questions we had were personal, belief, relationships. People would ask answers.com questions they would never ask their mother. I'm not even going to go into it. Can you get pregnant from, it doesn't matter. I'll tell you the saddest question ever asked of our system. We had 17 million questions and answers in our database. The saddest question was, someone one day asked, why do boys tell you they love you when they don't? Anyway, many of the questions were much more factual or much more scientific. We had politics, history, chemistry, you name it, religion even. But not all questions, you should realize, are simple factual answers. Some are opinion, some are expository. And we benefited from all of those because basically we were capturing data, textual data primarily, that would be used to build the engine.
It's actually crowdsourcing intelligence. So if people would ask their mother, or if they're too embarrassed, a rabbi or a doctor, exactly. Now they would ask the pool of
to the extent there was, because we weren't, just like Wikipedia, we could not guarantee the answers or the accuracy. In fact, those signals were reinforced by traffic, were reinforced by edits, were reinforced by scores. There were a lot of different ways. So our goal was to get the highest quality answers, but it's a difficult area. And I would say that we used some machine learning techniques to measure the question quality and the answer quality, but we weren't generating answers at that stage intelligently.
Could you tell by the way someone phrases a question, types in a question, what aspect of the answer, or what version of the answer that you have in your inventory they were looking for?
No, at that point they were just reading, and it's not, sometimes we would have many different versions. So if you had a question such as, when did World War II begin? Okay, that could be phrased many ways. When did WW2? When did the Second World War begin? And there were in fact many different aspects. Someone said, no, well, September 1st, 1939. Someone else said when it was this invasion. There are many different ways to look at something like that. But the goal is getting information. Nowadays, Google, by the way, does a fantastic job of giving a first cut at many of the answers. So not only can you ask the population of Athens, that's easy, but they're actually answering questions like, I wanted to know yesterday how to turn off shuffle on an album in my Apple Music. Okay, so they gave me a step-by-step thing. So they're doing much more. But systems like Quora and others are, certainly Stack Overflow in the technical area, are fantastic at gathering that information today. And when we sold Answers.com, we were well aware of where the industry we felt was going.
So really today when people have an answer, they go on Google, and some people even feel like they have a personal relationship with Google. They can complete their question. So I'm an hypochondriac. Google always completes my questions with a disease or some catastrophe. What do you feel the added value of a human-generated Q&A based system like Answers.com over a machine learning one?
It's symbiotic because Google is looking for information out there on the web. They also supply some of their own very well. But they're looking for information, and other sites are presenting data and text. So they're just Google is very good at connecting it. So I won't say that, I won't say that people go directly to, they do go directly to Quora and places like Answers.com, and certainly Stack Overflow. Nowadays they go to Amazon. Nowadays I might ask a question of Siri or of Alexa, but the world is developing to a place where people are just looking for very specific knowledge on demand.
What do you think, last question, because we're running out of time, what do you think the future of asking questions to get the right answers is? Where do you think we can go next?
I think there will always be a need, of course, for getting quick information at your fingertips when you want it, where you want it, how you want it, etc. So it may not be textual. It may be a little bit more where it's guessing in advance. Amazon is coming up with a system now where they're going to send you what they think you want, and you put in the box what you didn't want and send it back for free. So there's all kinds of different models for anticipating requirements and use. But it's a very exciting time in the industry, and we'll be seeing where it goes from here.
Just a word on what you're doing now. What's your next?
I'm actually enjoying right now talking to lots of different startups and exploring possibilities of advising them and helping them grow to the next level.
So thank you very much, Bob.
My pleasure. Thank you.